All right, so we should be streaming if this is working properly. I'm going to welcome Mike Mull here, who's going to present Hyperlog Log in Practice, an algorithmic engineering of the state-of-the-art cardinality estimation algorithm. So take it away, Mike.
So this first slide is just basically a quote from the paper by Philippe Flageolet describing the original version of Hyperlog Log. So I highlighted the words that are kind of important in what this algorithm does. I think the key things are it's an estimation algorithm, so it does not give you exact results, and it's trying to estimate the cardinality of a multi-set, so basically the number of unique items. And the other, I think, key point of this is that it's trying to do this on massive data sets, often streaming data sets where you only get to see the data once, and so you can't make any optimizations that would require storing the data and looking at it multiple times. Again, this is from the not from this paper, but from the previous paper, from the paper that described the algorithm originally. So, sorry, I seem to have. I guess it's the next one. So, one thing that's interesting to me about this particular problem is that for small data sets that don't change much, it's trivial. It's probably something that if you are a working programmer, you've done hundreds of times. If you are a SQL programmer, if you know relational databases, you've probably done a count distinct before. If you work with Unix, you probably run shell commands to do this very same thing, and it's pretty straightforward. I think anybody who is a working programmer could probably easily write a program to do this, and in fact, I've been using this problem as an interview question recently, just to see if people can write a simple algorithm to do this. So it's not a hard problem computationally. In most cases, you just need to see each element once. So it's generally speaking an order n algorithm in terms of the time complexity. In terms of the space complexity, it's also relatively efficient. It's most algorithms that you use for the exact solution are either order n or order n log n. The n log n usually comes from cases where you're sorting the data to do the computation. So, for small data sets, this is a pretty easy problem. The interesting thing to me is that when the data sets get really huge, it starts to become a very hard problem. As you'll see later, a lot of the cases here are cases where you really need to be memory efficient. So you're talking about sets that may have cardinalities of well over 1 billion, and so you can't store even a hash of that in a set in an efficient way. So why do we care about this? The first applications of this were primarily around database query optimization. So when the query planner is trying to optimize a query in, say, a relational database, if it knows the cardinality of the sets, of the tables, it can make better decisions about which table to join to which other table. So basically, this information is useful to the query planner in a SQL database. Another place where this is pretty common now is in monitoring of network traffic. So it's even built into the hardware of certain routers now. And the idea there being that if you see a strange change in the number of unique things coming into your network or going out of your network, it may indicate some sort of anomaly, like a DDoS attack or something like that. Another application in big data sets is what they call data sketching. I mentioned this earlier with relationship to that product called Trifacta. A lot of times if you have a big data set, you just want to get an idea of how big it is, how many unique elements it has, that sort of thing. There's a number of algorithms that are used for this. Things like count-min, Bloom filters are used for that, and hyperlog-log is one that's commonly used. In fact, I think somebody was telling me that Redis has an implementation of hyperlog-log built into it. And then finally, just doing data analysis. I mean, there's a lot of cases where you need to know how many elements are in a set. The cases that they talk about in the paper, this paper's from 2013, so the data sets are probably a little bit bigger now, and they've moved on from PowerDrill to BigQuery or whatever. But there's just people who are asking how big is this data set, and it may be because they're doing A/B testing on their website, or they're involved in marketing, or trying to improve their ad tech or whatever. And of course, their data sets are too big to count exactly. These quotes here on the slide are from the paper. There's the one that kind of caught my eye was that 100 computations a day yield a result greater than 1 billion. So there's people doing a meaningful number of queries every day on data sets that have a cardinality bigger than 1 billion. And that was 2013. So.
It's like searches on Google.com, for example.
Yeah, like unique searches. That'd be the kind of thing they're looking for. So there's kind of a lineage of this algorithm. The first ideas go back to a paper by Flageolet and Martin in 1985 that was mostly along the lines of helping with databases, and that algorithm or that method was called probabilistic counting. Many years later, I don't know why they took 18 years, but many years later they published this paper on what's now called log-log, and a variant of that called superlog-log. And then a few years later they published hyperlog-log. And Google, I think, probably to be both amusing and to distinguish their improvements, called it hyperlog++. As far as I know, there have not been any new versions of this algorithm with new names, but yeah. So the first, I think this is probably the key idea in this whole lineage of algorithms. This is from the 1985 paper, and the idea is what they call probabilistic counting. So roughly speaking, the idea is you take the item that you're trying to count, you compute a hash function on that item, and then there's something about that hash function that you can keep track of that will later allow you to estimate the cardinality. In the case of probabilistic counting, it was a bit pattern, and I'll talk more about that in a second. So basically what you have to do is you have to go through every element in your set and do this process to find the observable thing. In this case, it's you take a hash value of every element and you look for a particular bit pattern. And then once you've got all these hashes that you've calculated on the data items, you can use that in some way to infer the cardinality of the set. So again, the key element of this is hashing. So we assume offhand at the beginning that we have a hash function on the thing that we're counting, and it maps to some number between 0 and 2 to the L minus 1, where L is some arbitrary size that we want to achieve. In the case of probabilistic counting, I think it was 32 bits, and pretty much through all of the papers that Flageolet and his colleagues did, it's 32. So then we're going to assume and this seems like a fair assumption if you've studied hash functions, that the values that are generated by this hash function are uniformly distributed. It's not literally true, but there's been a lot of study on hash functions that show that that's a fair assumption to make. So if that's true, then every element of the 2 to the L minus 1 possible elements occurs with equal frequency. So the implication of that is that this first element, this first, if there are 8 bits, let's say, this first item with 7 zeros and a 1 will occur with a probability of roughly 1 out of 256, because there are 256 possible elements and they're uniformly distributed. Similarly, patterns with 6 leading zeros, a 1, and then either a 0 or 1 will occur with probability 2 out of 256, and so forth. So the thing that's sort of basic about this probabilistic counting idea is that there are certain patterns that will occur in the hash function with a certain probability, and the likelihood of encountering the less probable patterns increases with the more unique items that you encounter while you're iterating over the set. The pattern that they tend to use in these papers is the number of leading zeros in the bit pattern, but just to be clear, it doesn't have anything to do with the magnitude of the number. The fact that there's leading zeros, it could also be trailing zeros. So it's just the important thing is the frequency with which the pattern occurs, not where it occurs necessarily. Does this make sense? Because if this doesn't make some sense, then I need to work on it a little bit more. But this is kind of the basic concept underlying probabilistic counting. So the thing that we're trying to observe in the bit pattern, in the case of probabilistic counting, it was what they used was the least significant 1 bit in the hashed value. In the later versions of log-log and hyperlog-log, they changed that slightly to be the position of the first 1 bit. So what they're really looking for is patterns of the count of the leading zeros. But they call this function rho, and so it's basically just a very simple function that they apply to the hashed value, which returns the position of a particular bit. In the case of probabilistic counting, that's the least significant 1 bit. In the case of log-log and hyperlog-log, it's the sort of leftmost 1 bit. So in probabilistic counting algorithm, what they would do is they would calculate rho, and then they would set that bit in a bitmap. So they would have this bitmap where every bit would get set if rho function returned that bit as its value. So if the rho function returned 4, they would set the 1 bit the 4 bit in that the 4th bit in that bitmap, and so forth. And so at the end, they would have this bitmap that indicated everywhere that the rho function had returned the least significant bit. And then from that bitmap, they developed a statistical estimator that was, I think their description of it is the position of the rightmost 0, but I'm not going to get into that. In any case, they had an estimator that would give them an estimate of the cardinality. But the problem with that is that if they just do this once, there's so much variance in that estimator that on any given run through the data, it's going to be pretty, the chance is that it's going to be fairly off the actual value of cardinality. So one thing you could do is just repeat the process a bunch of times. That's sort of a non-starter because you're trying to make this algorithm relatively efficient, and if you've got a big data set, you don't want to do it enough times to get a reasonable estimate. So that's something they didn't even consider. The other possibility which comes to mind is that instead of calculating one hash function for each item in the set, you calculate a bunch of hash functions. Again, that adds quite a bit to the computational expense. And the other problem there is that right now there's no theoretically known way to generate independent sets of hash functions. So you don't really know if the new hash function that you've generated gives you any different results or results that are independent of the results you got from the first hash function. So the next solution is, instead of doing multiple hash functions, what they would do is they would take a certain number of bits of the hash and use that as what they would call a stream. So in my little picture down at the bottom, what I'm doing is I'm using the first, I think, 8 bits of the hash to indicate the stream. So they call this the index in various places as well too. So basically what you're doing is you're dividing the data set into a certain number of subsets. And then you're using the remaining bits to calculate the cardinality of that subset. And your hope is that the cardinality of each subset is roughly the cardinality of the whole set divided by the number of subsets. So this method they call stochastic averaging. And again, this comes into play in almost in every subsequent algorithm in this lineage. So log-log, hyperlog-log, and Google's hyperlog-log++ all use some variation of this. And again, it doesn't really matter if you use the first bits or the last bits. It's just you have some subset, usually at the beginning or the end of the hashed value, to use as the index into the stream. So, so the idea being then that you now have however many streams that generates. In this case, since it's 8 bits, you'd have 256. You now have 256 estimators of the size of the substreams, and you average over those to get a better estimate of the whole cardinality. The final algorithm that they come up with using these methods is what they call probabilistic counting with stochastic averaging, or PCSA. Again, this was 1985, you know, in 1985 I was actually programming, but I suspect a lot of you are probably not quite there yet. But you know, these weren't bad results for 1985, but they're not great. So with 256 substreams, they were getting about 5% accuracy on the estimate of the cardinality. And the memory space used was basically the number of streams times the base 2 log of the cardinality. So you know, quite a bit better than linear, but not quite where the later algorithms get you. I felt sort of obligated to stick this slide in here because there's a lot of strange factors in the later estimators for these algorithms, and it's pretty much beyond my capacity to explain where they came from, so I'm not going to attempt it. Flageolet was his main interest was in algorithmic analysis, so he was following in the footsteps of Knuth and all these guys who are looking at in very great detail at algorithms and how they behave in an average way. So not just large scale computational complexity, but how the algorithm actually behaves in the worst case, the average case, and so forth. And so if you read his papers on log-log and hyperlog-log, they're usually like 1 or 2 pages saying, here's this algorithm we created, isn't it cool? Okay, here's 15 pages of calculus showing you why this estimator has this alpha factor in it. So it's fascinating stuff. If you're interested in it, I recommend going to look it up. He invented a lot of these techniques. There's a thing called Poissonization and depoissonization, and this thing called the Mellon transform. And anyway, it's very complicated stuff. But all he's basically doing in that is he's accounting for the fact that the average that he's taking is not on a simple distribution. The distribution of these estimators is not, a simple normal distribution or binomial distribution. It's kind of complicated, and so he throws in these adjustment factors to give a result, a correct result. So in the case of the estimate of the expected value of the estimate in probabilistic counting, there's this phi value of 0.77351, and that later on, you get this estimate of the standard error of the algorithm, which is 0.78 over the square root of m. Both of those are, come from really complicated formulas, which I won't put up here. I'll show you the hyperlog log version of it later, but I didn't think this was important enough to explain in too much detail. Excuse me. So the next development was log-log. The really key difference between probabilistic counting, the stochastic averaging, and log-log is that they realize you don't really need to make this bitmap. All you really need to do is once you've calculated that value of rho, which is the position of the leftmost bit, all you really need to do is keep track of where that position was. So as that number of leading zeros becomes larger or smaller, you just need to keep track of that in a relatively small number of bits. So if you're trying to keep track of positions 1 through 32, you only need 5 bits. So in the log-log algorithm, basically what they're doing is the same thing that they were doing with the previous algorithm, except now instead of making this bitmap, each substream just keeps track of the maximum value of that row function. And since they're using 32-bit hash function, they only need 5 bits to keep track of where that bit is in the hash function. So, and again, exactly the same as the PCSA thing, when they calculate that value across all the streams, they just average it. They do a simple average of the values in the streams. And if you read the papers, you'll see reference to a geometric mean. The only reason why they call it a geometric mean is because they're doing an average of log values. So if you're actually averaging if you took out the log, you'd be doing a multiplication. So adding logs is multiplying. So the space complexity of log-log is log-log, hence the name. And I won't go too much into super log-log because the algorithm is basically the same. They made some sort of engineering improvements to get the error better, but the basic idea is very much the same. But super log-log is a pretty cool name. So this formula down at the bottom is the estimator for log-log, and again, it's got one of these magical alpha factors in it. But you can see that to the right of the magical alpha factor, it's just basically m times the average. So you expect each substream to have roughly n over cardinality over m elements in it. So you average those up and multiply by m, and you should get an estimate of the cardinality. So hyperlog-log, the really key development here, which probably doesn't seem that significant, is that instead of using the arithmetic mean, they started using what's called the harmonic mean. I suspect a lot of you have encountered this in other contexts before. The main reason why this was significant to the algorithm was that it increases the accuracy substantially. And there, again, I don't have the capacity to go into the technical details of it, but basically the harmonic mean reduces the effect of some of the right tail distribution of the estimator. So a sort of simpler way to say it is it reduces the effect of outliers. So if you have some substreams in here that are where the estimates are way off, the harmonic mean is going to reduce the impact those have on the overall average. So this formula is just the formula for the harmonic mean across the substreams. This is the actual estimator for hyperlog-log, which again is just m times the harmonic mean plus this fudge factor alpha. So it's very similar to log-log, except now you're dealing with the harmonic mean instead of the arithmetic mean. Alpha, very simple formula for alpha here. Let's see if I can, yeah, get here. Yeah, so that's alpha. The analysis to get to this form takes something like 12 pages in the hyperlog-log paper, and it goes through all sorts of crazy mathematics. But that's this expression basically converges, and again, it's dependent on m. So the value that they use in a particular case is dependent on how many substreams there are. I forget how many they were using typically in the hyperlog-log paper, but in the Google paper they use anywhere from 14 to 16 as the number of 2 to the 14 or 2 to the 16th as the number of substreams. As we'll see later, hyperlog-log, the estimator in hyperlog-log also has bias. So especially on low cardinalities, it has a pretty high bias. So what they show in the paper is that asymptotically, it has essentially no bias. So when you get up into higher cardinalities, the bias goes away. But in the lower end, it's got a pretty significant bias, and we'll see more on that later. So they added a correction in for lower cardinalities. They also found that when they get into really high cardinalities, they start seeing hash collisions, and so they had to introduce a correction for that as well. This is one of the things that the Google guys addressed. So finally, on to the topic of the paper, now that I've presented the pedigree. So the guys at Google, the data engineers at Google, have had a need for this type of algorithm. They have all these internal data systems for keeping track of stuff. At the time, they were working on this particular group was working on Power Drill. As I mentioned before, they get thousands, tens of thousands of queries on these systems every day. And at the time, before they started using this, they were using something called min count, I believe, which is another estimation algorithm, but uses considerably more memory. So their goals in introducing something like hyperlog-log was to make it still be fairly accurate. So their min count algorithm was fairly accurate, but used too much memory. Memory efficiency is a main issue of theirs. And in particular, they talk in the paper about how one of their goals was if they don't need to use as much memory as hyperlog-log would normally use, then they don't want to. And I'll talk a little bit about some of the optimizations they make there. The other thing is they need to deal with extremely large cardinalities because they do have data sets now which are well over 1 billion unique items. And then their fourth goal was practicality, so they wanted something they could actually implement and maintain. Which seems like a lot to ask. But. So the first improvement they make seems like kind of a no-brainer, and I don't really understand why they didn't make this same change in 2007. So basically they switched from a 32-bit hash function to a 64-bit hash function. They say in the paper that they use a proprietary hash function, but they also say that they experimented with various hash functions and it didn't really have any effect on the results. So A, this gives you the ability to handle much larger cardinalities without collisions. So that that seems like an easy win. And then second, because of the way that log-log and hyperlog-log work, by using a hash function that's twice as large, you're really only adding 1 bit per substream, really. So in normal hyperlog-log, it would have been 5 bits times however many substreams you have, whereas this is 6 times however many substreams you have. So it seems like a pretty small penalty to pay for a pretty big win. So the second improvement that they make is for estimating small cardinalities. And what they mean by small is kind of open to interpretation. Unfortunately, this graph is not really visible. I was kind of hoping it would show up bigger on the screen. You can sort of see that there's a diagonal line there, which would be, what an ideal algorithm would do, and then this red line that kind of curves down toward the left-hand side is what hyperlog-log would give you. And so there's a pretty substantial bias, and I think the number where that starts to become really significant is, I've forgotten what it was. I think it's around 60,000, yeah, something like that. So, again, their approach is just to take hyperlog-log and engineer the heck out of it. So what they do is they just do they do experiments basically to figure out how much the bias is at that range of cardinalities. And so they just run a bunch of experiments at each cardinality, and what they figure out is they take an average of that and figure out what the bias is for that average cardinality. And they essentially store that. They say they store 200 points. So when they're actually doing real cardinality estimation, it's an estimate, so you don't know what the actual value is, so you can't just go look it up in a table. So what they do is they have these 200 interpolation points, and they take the 6 nearest neighbors to that and do an interpolation on those 6 nearest neighbors to get what their estimate of the bias is. So again, this is basically to correct the bias in the hyperlog-log estimator over this one particular range of cardinalities. So this graph kind of shows, I think I got my numbering wrong, but this should actually be improvement 3. But it's actually, I guess, 2B, 2A and 2B. The other thing that they do to improve the estimates on low cardinalities is that at certain levels of the estimate, they just switch the algorithm. So this is straight from the paper, and you can see that the green line, the dark green line, is the error in an algorithm called linear count. So that's, I'm not describing that here, but it's another cardinality estimation algorithm, which gives them, at low cardinalities, gives them considerably better estimates, but takes up more space, so it's not useful for much larger cardinality situations. And you can see here, the blue line is their bias-corrected version of hyperlog-log. And you can see it, where this vertical line is the point at which those two things sort of cross over. So if their estimate is below this line, they just use the linear count algorithm. If it's above that line, they use their bias-corrected version of hyperlog-log. And you can sort of see that above, as Chris was saying, about 60,000 or so, hyperlog-log and the bias-corrected version of hyperlog-log essentially give the same results. So the bias sort of disappears above those cardinalities. This next set of improvements sort of impressed me. I mean, they really put a lot of effort into making the, to me, the idea of 6 bits times 16,000 channels didn't seem like a lot of memory, but apparently to them it is. So they made a lot of optimizations to use less memory. And so the first approach they take is what they call a sparse representation. So instead of allocating a certain number of bits for every possible channel, they just essentially have this mapping of, for this index, this is the current row value. If you haven't seen the index yet, if you haven't seen the index for one of these 16,000 streams that they're using, they don't store anything. It's only when that index is encountered that they add an element. So the way they actually do this is they encode the stream number and the row value into an integer, and they keep that in a sorted list. And then they have a secondary auxiliary set where they just insert things while they're scanning through the set. And so if you look closely at the algorithm, what they do is at some point when the set gets too large, they kind of pause and they merge that into this sorted list. So ideally, the sparse representation is this sorted list that will only have the elements where the index has already been encountered. So the other detail of this is that as they're going, if they reach a point where they've now found most of the indexes, they have to convert from the sparse representation to the normal dense representation. So there's code to do that as well. One of the really interesting tricks that they do is because they're using this sparse representation, and then they're not using as much memory, they can use greater precision. So the normal case is they use 2 to the 14th subsets streams, but in the case where they are using the sparse representation, they can actually use many more bits to keep track of the precision. So I think they say they use 25 in the sparse representation. That was all about that one. So to make it even more compact, they do 2 other things. One is they compress it. So if they've only reached a certain size on the value of row on the counter that they're keeping for each substream, they don't retain all the bits that they would need. They just retain the bits that they need to store just that number at that point in time. This sounds like it would be kind of expensive computationally, but they don't have to do it on every hash. So I think it sort of comes out in the wash. They also use difference encoding. So instead of keeping track of actual counts, they just keep track of the difference between the current count and the count of the next element. So the difference will be smaller, so they need fewer bits to keep track of the size. And again, since they have to scan through the list anyway, they can keep track of that count. This encoding part kind of amazed me. I just didn't think the memory issues were that big of a deal, but apparently they were. Excuse me. The other thing that they discuss in the paper is that when they are using the sparse representation, what happens in most cases is the point at which they switch between the sparse representation and the full dense representation is usually at cardinalities so low that they're going to end up using the linear counting method anyway. And the linear counting method doesn't need the row value. It just needs to know how many streams are 0 and how many streams have a value in them. So in this in this version of the encoding, all they keep track of is the index and whether or not they need the row value. So they only need one bit. If they if they don't have a row value for that index, they only need to have a bit saying, no, we don't know yet. Excuse me. So that's pretty much it. This is their final comparison of hyperlog log versus hyperlog log plus plus. So the blue-green line is their cardinality estimation with their algorithm, and the red line is the cardinality estimation with hyperlog log. And you can also sort of see this range here in blue-green is the 5th and 95th percentiles. So, you know, basically the range at which you're within you know, a couple, 2 or 3 standard deviations of the real value. So there's a couple of interesting features here. One is that their error is much better on this range here, and that's because this is where they're using the sparse representation, and so they can use 2 to the 25 substreams to average over in this sparse representation. So they actually get much better accuracy than even their own bias corrected version in this lower range. And then the other part that's kind of weird is that hyperlog log seems to have an aneurysm right there in the middle of that range. The way they explain that in the paper is that in the hyperlog log algorithm, they arbitrarily pick this threshold of, I think it's the number of the cardinality has to be, it's like 5 halves m or something like that, 5m over 2 or something like that. The problem with that being that that threshold is, when you're doing estimation, that threshold is kind of vague. And so in this is the part in hyperlog log where they switch the approach they use. But since they're doing estimation, they don't really know where that boundary is clearly. And so in that small range there where they're switching between one algorithm and the other, their variance explodes. And the hyperlog log plus algorithm pretty much smooths that out. So I hope that was not too short. I figured it would probably be fairly dense, so I didn't want to make it too long either. But yeah, if you have questions, fire away.
That's a lot to absorb, and thank you very much. So round of applause.
Does everyone have questions? Hold those in your head. Don't forget them. I want to take a slight detour and do a little round of quick introductions, and then if anyone's looking for a job